Hello guys, how are you doing? Are you having a nice evening today? Okay, just please raise your hand who was here 2 years ago at Moscow 2017 and saw weird C# at the time. And anyone from St. Petersburg last year? Oh, we have like few guys that really like to be hit by strange stuff. Okay, I'm going to give you a bad news now. If you thought that the very first talk was a little bit weird, this gets even worse. So, today we are going to be talking about metaprogramming. Okay, start it again. We were going to be talking about metaprogramming, and we are having issues with the monitor for some reason. So the idea here is we are going to start with some facts. And what I mean by facts is things that we knew for a long time ago, and it's not something that is pretty new to any one of us. First, metaprogramming. As you know, metaprogramming ain't a new concept. It has been around with us for like 60 or 70 years, so it's 60s stuff. The very first language that actually implemented metaprogramming was Lisp. I don't know if you know this joke, but it's like a pretty common one when you talk about something that has been around for like 60 years. So the thing is, as metaprogramming has been used for language like Lisp, where even data and code is exactly the same thing. We have been seeing it being introduced in different fashion. You can, if you have anyone here programming in C++. Okay, I see a few, and in Python. I was expecting a little bit more there. There are different versions of different ways that metaprogramming get put into the languages. So the thing is that for C#, it was really not designed up front to have these metaprogramming capabilities. It only along the time that it got incorporating generics stuff first, then functions, actions, and it started to look a little bit more functional in a sense. Because metaprogramming, in a sense, is one of the things that make functional functional. So the interesting thing, though, is that the runtime do support metaprogramming. So it's a question of if the language allows us to access the capabilities that the runtime already has. And the reason is simple. F#, it's able to do metaprogramming. It's been implemented. C++ CLI, also, the runtime supported. What, as you know, is at this moment is because some of you have been on my talk before, we had to go a little bit some steps to actually figure out how to access those capabilities. If you asked me 2 years ago about that, I would say I don't have a clue how to do this. It just works. Okay. Now we have been able, after 2 years, to figure out at least some common patterns that are usual when you try to unlock that capability. So without further ado, this is a rated H talk, and where we are going to see some assembly. Sorry, I was expecting to show some more assembly, but I didn't have time to go so deep. Definitely, we are going to see an intuitive code and some C# that barely resembles C#, by the way. So the question of why we should love metaprogramming is pretty simple. Metaprogramming has always been used to define reusable behavior. If you look at C++ STL, if you look at the ability of Python to actually modify its own runtime, or even Smalltalk. The interesting thing about the C# and the .NET Runtime, it is also allow us to generate code, which is relatively fast, if not convoluted. So it's difficult code to write, it's difficult code to maintain, but it ain't that difficult if you compare it with the kind of stuff that we actually saw in St. Petersburg. So even though today I'm not going to show you any state-of-the-art speed for any one of the algorithms that we are going to look at, the idea is that we still can get 80% out of 20% of the effort that it took us to optimize a single algorithm. As I mentioned in Scratch Metal, it took me around 2 weeks to actually get to the point where there's no improvement you can actually do to that because the processor memory speed will not allow us to go farther. And the interesting thing about this kind of code is it is so convoluted and it uses specific things on the just-in-time compiler behavior. When we find something here, the just-in-time compiler engineers just love it, really. And before we start, there has been one question that was very interesting on the first talk that I did on this topic, which was at the end someone asked, if you're around, raise your hand, because that was a great question, by the way. I was asked, if you are exploiting how the just-in-time compiler works, how we are guaranteed that this continue to be so, that the kind of code that we write today is actually going to be useful tomorrow. And at the time, my response was, we don't. That's why we keep looking if in the process something breaks. Well, 2 years have passed since that time, and I can tell you one thing, which is a relief in a sense. It is, at least the just-in-time compiler didn't get worse. In most cases, it actually gets better. So if you ask me today the same question, I would say, don't worry. If it works now, it's probably going to work later. So the interesting thing about this approach, in which we are going to write code that probably at the first time is not going to be so idiomatic, is that today we have like two main sources of design. In your design space, for any software that you are going to do, you have two main sources. One is inheritance, and the other one is aggregation or composition. Metaprogramming now, which is enabled, that the very first thing that you would say this is metaprogramming is generics. The base generics, when you have a list of T, it added an extra dimension. But the thing is, you can go further than there. And this is what we are going to talk about today. So from the earliest talks, I need to refresh two key concepts. First concept, if those that have seen the talk may have remembered this graphic, where we have been steadily improving the algorithm to the point that we actually maxed out the memory bandwidth. So it doesn't matter if we write this code in assembler, we are not going to get anything from it. But on the other hand, I mentioned also, you know what? You see all this stuff, we still use this one, with a scalar code, no vectorization at all. And the reason why we do that is not because it ain't faster. It's because this thing is still manageable. Because there's a senior developer can actually go and look what this thing is doing and actually understand it. The other one is faster, yes, but still, this one can be maintained. So the problem with highly optimized code is when you optimize code, you have to be sure that you want to go in that direction. The idea of the techniques that I'm going to show you today may not solve that issue, because at some point you will have to decide, I want to go in this direction, ergo, I'm leaving people behind. There's people that were not being able to touch this code anymore. And for a reason. But we still can get decent code, like understandable code, without obviously reaching those levels. If you need to go to those levels, it's a conscious decision. Even if you need to go to this level, it's still a conscious decision. It's a decision that has to be part of your business goals. You're not going to start on this journey just because. You're going to start on this journey because you have no choice. Okay? This was the second most important. This comes from the first talk. In the first talk, one of the important things is that we have structs, and structs has a very different way with how they are treated by the just-in-time compiler if you compare it with structs. A value type is something that you use and that it has certain specific rules that you can abuse to actually do stuff. In this case, what we are looking at here is we are defining strategies that they are structs, and because we are returning constants, we are propagating back those constants, and that generates a very, very interesting effect, which is it deletes code that it's never going to be executed. So today we will focus on the step-by-step. I could still say trying to reach the ocean without hands from a rocky terrain, and it could be true. But let's focus on the step-by-step here. The idea of today is we are going to see 3 examples, just 3 out of the 6 or 7 techniques that currently exist. Why we are choosing these 3 techniques? We are choosing these 3 techniques because they allow you to cross-use them, to mix them, to achieve interesting effects in the code and show how you can modify your code when it gets executed in such a way to achieve high performance code. But I'm using it for high performance. I am actually looking to show you these techniques so you can tell me in where else we can actually use this. I don't know. I use it for performance. So I decided to use a simple, like the most boring example that I can actually get for all examples. So the example is not what is interesting. What is interesting is what will happen with the example. So to start, we are going to start with a binary tree. Anyone knows a binary tree here? I see a lot of hands. Nice. And the technique we are going to use with this binary tree, it's a method strategy. In some sense, similar to what we saw in that slide, but we are going to do all the steps. We are going to start from the basic code and see how we are going to implement the method strategy to actually achieve our goal. So we are going to start with something very, very simple. We have here our node. It's nothing to see here. There's a value. We can go on our left side. We can go to our right side. Simple. Our tree starts from the root. Nothing out of the ordinary. We have our insert code. Nothing that you haven't seen before. And we also have a traversal. We are going to focus on this particular method because it allows us to showcase this technique. So essentially for a traversal, what we are going to say is some may have noticed that there's no action here. I am traversing the tree and I'm not doing anything, right? Because the interesting part is not the act. But if you put something here, you can actually do the actual part of the acting when you traverse the tree, doing something, like write to the console or whatever. This code is, anyone see anything strange on this code so far? So it's a general no, right? Yes, it's as boring as it can get. I think that if I could try to find some more exciting code, probably I can't. If someone can figure out that most boring example, I'm all ears. I want to hear. So, if someone comes and say, hey, you know, what I need is, I need to be able to give it like a little bit more life to this. Okay, it's like, yes, that code is great, but you know, I need to be able to modify it. I don't want to always go to the left side and always go to the right side. There's two options. Either I write the code inside the traversal tree, which is one way, it's fine. And the other way is say, okay, I'm going to externalize the problem and give someone else the responsibility. This is plain object-oriented programming. Someone else the responsibility to figure out what to do with it. So let's say that now what we have is a traversal strategy interface. Okay, this traversal strategy interface is going to tell me, hey, you know, I want to first go to the left or first one to the right. This is like the basic traversal decision. And we are going to implement our infix strategy, which is nothing more and nothing less than say, hey, you know, I'm going to the left and then going to the right. And the thing is that calling this code is like simple. We just traverse from the root and be done with it. So this is how that particular code goes. Anyone see anything strange in there? So because so far until the strategy, there's nothing that really looked like odd. Raise your hand if you don't see anything strange. I have one, I have two. Okay, yes, I have like 5. Yes, there's nothing strange. Not yet. So let's look at it. Let's zoom into it. As you can see, there's like 4 different sections for the code. Okay? So this is a type. This is our strategy type. But you remember that was not our interface type. This is a type, something. And it's also a struct. You remember what I said about the structs? They behave differently. They're like special. So because this is an struct, what would happen? What would you think will happen if I define a default and it's not an struct? I hear here, null exception, and you're right. This would just throw an exception and crash your program. But wait, this is an struct. What happened here? We have actually instantiated a method, a variable. And the thing is, hey, you know, we are using it in this section of the code. If you look at it, here's our strategy. The explosion that you would have here if not for the struct would be like terrible. And now what we do is we actually traverse again, doing the same thing all over again. Now, this pseudo-instantiation is interesting because it has been instantiated. There's a variable out of it. But what happens if your struct doesn't have any field? Where do I put the variable? Nowhere. But it exists. Kind of. And this is where things become interesting. Because that kind of is the very same thing that you are going to use to do this kind of stuff. Because you can instantiate in things without the actual cost of instantiating things. And the just-in-time compiler will know that this has certain type, but the only thing that will generate for that type is the method table, which is internal. So you are giving to the just-in-time compiler information to actually do stuff, but still, the just-in-time compiler will not generate any code for it beyond when you call that method, you are going to point to the proper place. So what do you think? I want you to raise your hands if you believe it is, and keep it down if you believe no. My assertion here is that this yield version is within 50% upper or lower from the original code that we wrote. So let's say that it cost 10 milliseconds or 10 seconds. It does. I don't care. 10 seconds for the original code. So this is going to be between 15 and 5. So raise your hand if you think that's true. Okay, so half the room. More or less what I was expecting. Random. Nice. No. The question is why? The interesting thing about this is, if you would have said me 2, I would think. If I would say 4 times, probably I will have everybody here raising your hands. But it's not even that. It's more than 10. 14 to be exact. Where did that come from? Any idea? The yield, yeah. The machinery behind the yield, the state machine that you need to actually do the yield, is what you are measuring here. This is the difference between the 28 and the 300. And the reason why it is so is because yield is good when you have 2 conditions. You are not calling it much. And second, the size of the operations that you perform with yield is big. I said here, act cost 0, because we don't even have it. If we would have to go to disk, who cares about the yield, right? But because I come from a place where high performance is a thing, it's something that it actually drives business objectives, this is not enough for me. So we need something else. So we know that enumerate is out of the question, because anyway we create an enumerable, we are done. But we can still do something. And here comes the magic. This is the magic trick. As you can see here, this is a kind of a recursive type, because you have your type being defined, which is your interface. And at the same time, you have yourself defined here at the method level. So what is happening here? I will have this method that will take someone like me as a parameter when I get executed. This trick can also be used on matrix, but it's a little bit more convoluted. Sorry, on class, but it's going to be a little bit more convoluted. The idea here is that what you need is something like this. You need to say, hey, you know, I will traverse this tree in such a way that if my strategy, which I am instantiating at this time, I'm going to go on this side or I'm going to go to the other side. So this is my strategy. This is my infix, okay? But I am defining it in terms of myself. What happened here is that my infix strategy is going to call itself with a type, which is itself. And because these are value types, what the just-in-time is going to see is that infix strategy is calling a method of himself. The struct itself, we just call recursively on himself. The interesting thing is that the color code, which is what our users use, is exactly the same. There's no change. Now, raise your hand if you think this solution is gonna get on the 50%. Good, non-random. I do not see faith in you guys. There we go. If you see, what we have achieved here is a suboptimal version, because it's always optimal to go and write the code by hand, okay? It still have very good performance, and it still is able to accommodate the original goal that the yield version was expected to. So we were able to bake the cake and eat it too. That was example one. That shows you that you can actually generate types that are defined by themselves. So they use their own type as part of the definition. And it shows you another thing, which is you can actually instantiate these things without causing any allocation of any type. So they are virtual instantiations. What we are going to do to show here is another simple example, which means I'm a performance guy. The very first thing when I have to do mic optimization is, hey, you know, why don't you try to unroll this loop, right? If you see a big loop, the very first thing that you do is, hey, let's unroll it and see what happens. But the problem is, unrolling loops, it's complex. It takes a lot of time to actually say, okay, yeah, I need to unroll this. And now I have all these dependencies, like what it used to be like a 10 lines code become like 70. It's a mess. And I'm just trying if it works. You know? So I'm an entire day just to make sure that I'm building the code in the exact way that it was supposed to be. Just to try it out, and it doesn't work. So the idea is, what if I could have some facility? And this is a question for you. What if I would have some facility that even if it's not optimal, would allow me to more or less achieve the same goals? Like, hey, you know, I will write these 10 lines of code and still get unrolling for my loop and see how good it goes. If it's really good, two things can happen. Either it doesn't work, or it works, or it's worked, and there's a third thing, that is, it's worked good enough. If it's good enough, why I'm going to prove it? So the technique we're going to see now, it's code pruning. And it goes like this. Let's say that you have this loop, you know, more boring impossible. assigning the index. The assumption here is always that this is divisible by 8, so there are no corner cases when we try to actually unroll this, okay? This is the unrolled version of that loop. You can actually now see the difference. And this is interesting because if you look at it, if you look here, and if you have been on Dan's talk, you will recognize that code. That's vectorial code. So the JIT was actually good enough to actually figure out that, hey, you know, I can do this in a big fashion. I can use big stuff. Some sort of big stuff. But the unrolling, if you think this is an unrolling of factor of 8, what used to be one single line now is 8 lines with a lot of indexes and offsets. Think about what it would happen if instead of 1 line, you have 10, and you need to unroll. You get the idea? So the interesting thing about it is, if we look the code like this, it's not showing us anything. But what if we do this? When we do this, we actually see 2 things. We actually see a space, which is the moment that you step to the next operation, and you see an act. This is your step. This is the empty line. You have 1 line that is empty, which is actually doing the step. It's a nap. And this is your act, which means I'm going to take the index and put it in the data. So anyone here thinks that I can define, and this is a trick question, you are going to say yes, but anyway, I'm going to try. I can define an unrolling method that with that, only those 2 methods in an interface is able to do unrolling by hand? I get a yes there. Okay, like 5 or 6. You don't have faith in me now. So let's start. Let's say that I want to do an unrolling by 2. We are going to use small numbers because if not, the code is going to be ugly. So we have these 2. We are saying, okay, you know, the step is going to be 2. And the action is I'm going to take the index and I'm going to put it in the data. Interesting thing, I use a ref float here. So I'm giving you the exact memory location. You can actually do other stuff in there, but it's more or less the same. The generated code is going to be the same. And we are going to execute. Which execute is simple. Essentially what we are saying is, you know, execute unroll with this guy that we just defined. We are going to use a float array. And hey you, this is the float array. Anyone think that knows how this code looks? How many lines? Let's start from there. 4 lines. Do I get 4 lines? I get 4 lines there. 7 lines. I get some 7 lines. 10 lines. 50. Okay. There's some people that are still not convinced. So this is how we write it. Let's say that it's around 20 or something. The idea here, as you see, is interesting code. I just cut it down in here, as you can see, but it's pretty easy. It's pretty easy to figure out that when this one is 2, the next one is 3, the next one is 4, the next one is 5, and so on until to 6. The interesting thing about this is that it's not such a complex code. We went from unrolling this stuff to say, hey, you know, I'm going to act, I'm going to step. I'm going to act, I'm going to step. I'm going to act, I'm going to step. Hey, should I step here? This is what we change. This is the key of this algorithm. But we are going to go step by step just in case, so I don't miss you through this code. Let's start here. This is our method. We have execute and roll. We have a type that essentially defines our configuration. And we have a type of the kind of things we're going to be dealing with. And obviously, as you may have already figured out, this is a struct for a reason. Now we have this. Anyone recognize the first line? Do I get a yes? Yes, I see many yes. Yes, the first line is a pseudo-instantiation. We are instantiating a type. It just doesn't exist. Anyone recognize the second line? I get some. Okay. Second line is interesting because, as you have seen it before, it's a constant. It's 2. And because it's 2 bigger than 8? No. So what will happen if you evaluate this? It will always say what? False. And when something is false in an if, what happens? It's never executed. And if it's never executed, what does the just-in-time compiler does? Drop it away. You have one there. And then we go to the real interesting stuff. Because all the other were just to set up for this. So we have 4, right? We are going to step how many times? You remember the code? The original code was? How big our step was? 2. So whenever it says unroll.step in your mind, just take it out and put a 2. So now what we have is for I equals 0 until I is less than data.length, we are going to increment I each iteration by 2. Simple. We are going to act on I, which the first time is 0, and we are gonna check. Hey, you know, is the 2 equals 1? No. Okay, we're going to continue. We are going to act on 1, which is 0 plus 1. Is 2 equal to? Yeah, it is. Can you think how this code will look? Anyone want to guess? This is how the JIT look at this code, okay? The JIT is gonna figure out this is unroll action 2, this is a float, and we got this. But because of all the rules, optimization rules that get applied, this is what happens. All the gray code go away. And because it go away, essentially you have an unrolling factor of 2 being executed here. We are within the manual unroll 8, right? Anyone see something fishy? It's slower. What happened? Bound checks. Bingo. Bound checks. The just-in-time compiler is able to figure out that if you are going to increment by 1 and you're going to stop at length, why would I check? Right? Well, it turns out that it did this on purpose. I'm going to give you a repository with all these examples. And you can go and build the faster version. It's just 2 lines change to get the fastest version for this. So take it as a kind of exam question. go and try to build the fastest version for this. We are going to yet another boring example, which is matrix. Who haven't used matrices before? Who haven't? Okay, almost no one, almost. We are getting there, we are getting there. So the technique we are going to look now is for interface de-virtualization. And the interesting thing about this particular technique and why I choose it is because we are not going to the method level in this technique. We are going to go to the type level, to the class level. We want to use the classes. So let's define our boring matrix. This is pretty simple. We have the bounds, the size for the x side, with size for the I, the actual array where we are going to put the stuff. Nothing new to see here. We have a constructor where we can create this matrix in the size that we want. We are going to create the backing array behind. And we are going to do, anyone recognize this? This index? This is row-oriented, row-first accessing. For anyone that has worked in mathematical code, you know that there's two different ways to represent there are many, but there are two main different ways to represent a dense matrix. One is you first write the x's and then move to the next y, or you first write the y's and then move to the next x's. So essentially, you are looking at it like this, or you're looking at it like this. The thing is, some algorithms work better on one, and some algorithms work better on the other one, on the other representation, because of how memory gets used. So the pattern of how you use your memory. In this case, I choose the row because if you are going to access it like linearly, I want to just go one line at a time. It's faster to actually do it by row than to actually doing it by column. But if you go to the code, there's actually an implementation for the column too. So if you try to abstract away the concept and say, you know, yes, I have the matrix, but I want to be able to say the storage is a thing that I can't change. What you could do? You definitely define an interface which serves you to do that stuff, to say, okay, no, now I want to create this matrix as a row, or now I want to create this matrix using a column version. So essentially, you will have three different methods in your interface. Initialize or create, you will have get, and you will have set. Simple as that. The thing is that if you do this, and you use the following things to benchmark it. You go and say, no, I don't have a class, I don't care. What I want is I'm going to write 2 for loops, and I'm going to access an array, no abstraction. You actually get 12.91, which is there. On the other hand, is I say, oh, no. I'm going to code the very first matrix, that the one that it's only row, and it's going to use the array directly. And I'm going to get 1382, which is fine, which is good. Because you are not that far away from the actual optimal, which is like, I am accessing the memory directly. But if you want the flexibility of actually being able to decide how you want to store your data, it skyrockets. That's 4 times. If you are doing mathematical code, that's bad. That means multiplying by 4 your cluster size, just because of this. So what we are going to do is to do something different. We know we can use the types to actually do stuff. And we know that if those things end up being structs, things are different. So what we do here, we bake in the type directly into our type, into our matrix. So what we do is essentially define our matrix, define our interface in terms of T, and use those to actually work the problem around. So if you see, the only difference between actually doing it by interface is this. You are going to say that you have a matrix here that has a storage type, and that storage type is also implements this interface, but it's a struct. So now you have your storage there, which, differently from our pseudo instantiations of before, this guy has meat. This guy does exist. But you could do this even if it doesn't exist. So in those cases, what you will have is this difference between the other one and this one. But the interesting thing is what happened here with T. The T get chained along the way. This introduced an additional problem. What now if instead of a matrix of T storage of T, I want to have a matrix of T storage of T? Now I have two T, probably inconsistent between themselves, because I can say float on one T and I can say byte on the other one. Okay? So this is a major problem, and this is why trying to do metaprogramming in C# is hard, because the language forces you to define everything beforehand, and it's not able to infer the types as C++ does. So whenever you start stacking these kind of types on top of the other types, you're actually starting getting very complex dependency chains of types. And now your user, the one that is going to use your code, actually have to deal with those. So there are solutions to that problem. We are not going to talk about it. It's called composition. To those that really want to know how this is done, at the end you will have a slide where there's a link to some code, to some experimental code, which is from where all these come from, which is a memory allocators library that is able to do composition between allocator types. So if you want an arena that also has a pool, you can actually build the two through composition, and then you have a pooled arena. If you decide that the arena is not good enough, you need the straight access to the hardware, you just put a native allocator in there, and you still have a pooled allocator. So the concept is that you can do all that through composition. But for that, you need to write certain patterns and the code in a certain way to achieve those. I just wanted to tell you, it's not free. So what we would like to write, this is me thinking to the future. If I would like to write this kind of code more, I would need to go to the C# guys and ask them for higher order functions, which would be great. It's probably not going to happen in the near future. Though there are alternatives. One of the alternatives that I laid out for them in a proposal, which is implicit. The implicit one is basically says the following: hey, at the point where I'm defining stuff, so as a user, when I say this, This is essentially already defined. Every type in the system has already been fixed. Because if I have a raw storage which is using floats, I cannot mix it anyway because all those t's are going to be floating around until it finishes up generating the code. So you can actually say, okay, you know, I want a matrix that has a storage and it has a t-type. Now the t-type actually is implicit in storage. So if I define it in storage, I don't need to define it in the type because I already know who he is. And because I already know who he is, everything is already defined. You don't need higher order functions. So just because we all want to see this graph to know how good we were with the template example, you can actually see it's not that bad if you look at it. And you are still able to change the underlying backing array behavior. So as I mentioned to you today, these are just 3 techniques. I want to hear from you. Seriously, I'm pretty certain these 3 techniques, or the 4 or 5 that you will find, are not all that there is. This is the part of the design space that I was able, because of what I was doing, to explore. Someone that saw the draft of the talk mentioned, hey, you know, you could actually go and build a NuGet library just to have the unrolling stuff. And my response to that is, yes, I could. Problem is, I haven't explored the design space to know what the proper signatures are. I'm pretty sure there are 4 or 5 signatures that you need. And whenever those 4 or 5 signatures are already there, you can actually build a library out of it and forget about the typical unrolling work forever. The problem is, I haven't explored the space as much to actually say, you know, these are the 5 signatures that we need. Whoever does that, have my blessing. So, if you want to know more about this, you have the allocator experimental branch. All these techniques came from here. If you look at that code, you will have all allocators, and there's allocator point something. You will see from thread-aware allocators, pool, and the idea behind all that is that you can actually mix and match the allocator types and achieve new behavior, and most importantly, efficiently. You are only getting the code that you use, no more. Which is what is important for high-performance computing, which was my aim for this. Also, some of the code, in the examples that I'm going to make available on the repository, which is called Metaprogramming, under my user, what you can look at it, what you can look is, I already left messages about what assembly gets generated and how the assembly change whenever you do. There's more examples than what I actually showed. There's 2 and 3 levels more of what I'm showing here. So you can actually go step by step and try to figure out what are the differences and why it was so, and why it generated the cost in the code. Before you leave, this is the caution part of the talk that I always give on performance talks. That you have learned how to do this doesn't mean that you have to apply this blindly. And I'm serious with this. If you have to apply this kind of techniques, it's because either you are experimenting with something and you just don't care, so no one is going to use this in production, hopefully. Or you actually needed it. You actually reached the point when there's no escape than optimizing. And at this level, Now, if you reach that level, this kind of techniques will allow you to have cleaner code than if you actually go the manual stuff, if you find the right abstraction. But to me, the balance between performance and code maintainability is the key to success whenever you have to go this path. For my work, I would first always go with this kind of approach until I really end a point that I cannot. Why? Because the difference is between having like 2 persons that can actually maintain the code against 5. It's a big difference, even though with low numbers. Okay, the other 20 won't be able to actually touch this code, and whenever they touch this code, they know they are risking a code review, which is fine. But the ones that really are able to touch the code with this approach is 5. If you go full optimization mode, like the kind of stuff that we did in St. Petersburg, probably there are 2. That's life. That's how it works. So always take care of how you do this kind of stuff. Always try to avoid it as much as you can. If you don't have choice, it's glad to hear from you any question that you have. In real life, I mean, you can just pin me on Twitter or send me an email. I have this problem. I don't know how to solve it. And I would be more than willing to help you. But it has to be like, I need this. So with this, thank you very much all for coming. Hope you enjoyed this. And let's have some high-performance code around. I believe we have 2 minutes, 2 minutes and a half for questions.
Yeah, we have time for 1 question here.
Any questions around?
No. So.
Good. I'm going to be anyway in the discussion room when we're going to actually use a Blackboard.
Thank you for the talk. Question is why we still use C# instead using C++, using DLL import for
normal question. Okay. Yes. Why would you use C# instead of using C++? For a project that I need 100 people in C++, I can do it with 10 in C#. Plain economics. Now, if you need to pay an expert on performance, you will need to pay an expert on performance, either if you're doing C++ or if you're doing C#, so it's going to cost a lot anyway. Seriously, it's plain economics. For some things, you still need C++, and I would use C++ anytime when I am in those things, when I have to solve a problem like that, without even thinking. It's a question of abstraction. If C#, the thing is, C#, the question is, isn't C# about zero-cost abstractions? No, definitely no. You are gonna pay for your abstractions, and it's fine. That I'm showing you a way you can actually get away without the cost is a entirely different thing. I'm showing you it's possible if you are willing to pay for the complexity of it. It's the same thing in C++. If I can give any random developer out there a problem to solve, I'm going to get a sample of all the potential programs that you can actually write in C++. 99% of those will have costly abstractions.